Okay, so it's 11 o'clock. Good morning, afternoon, evening, everyone. Welcome to this first seminar of the season. It's my great pleasure to welcome today's speaker, Patrick Mesana. Patrick is finishing his PhD at HEC Montréal in decision sciences. In fact, he will be defending his thesis on October 8th, if I'm not mistaken.
That's
So
correct.
this is a last chance for him to practice
Hmm.
uh, his work. I guess this is the last chapter of the thesis, and we are very happy to have you today and to listen to some Shapley value apparently, right?
Yes. Thank you, Professor,
Okay,
for
Patrick, the floor
yeah,
is yours. Yes.
yes. Thank you, Professor, for inviting me to present and to practice one of my chapter of my thesis. I did three different chapters, and I decided to use game theory for this chapter. I'm not an expert in game theory, so this is why I was very interested in presenting in this community because even if it's a work that is part of my thesis, I'm planning to continue this work, and you'll see that we have interesting results, but we want to continue after. So it's entitled Data Valuation via an information disclosure game. Typical plan for today. So an introduction on um, a bit of context. What is data valuation? What is the problematic in data valuation that we wanted to tackle, and our approach to tackle it. Then a bit of background, so more details, technical details on data evaluation, and also on differential privacy, because this is another tool that we used in this work. Then I'll give also more details on the methodology, and I'll show you the experiment results, and we'll conclude. So the context of this work is of an organization that collects personal information to create value. So in this context, we're mainly interested in organization that wants to build a machine learning model on personal information. But organizations these days, they also have to manage data, manage privacy, and they're subject to regulations. So you probably have heard about GDPR, and here in Quebec, we have something that is very close to GDPR that is called le Loi 25. And so I'm not going to give a course on what is privacy, but most regulations at their core have this idea of the right to be forgotten. It was introduced in regulations in the US in, I think, 80, 90, something like that by Warren. And it's still at the core of regulations and legislations. And it has been declined in more specific principles like opt-in consent, so you can't collect personal information without consent, and also what they call data minimization, which is limiting the collection and of data, and also purpose limitation to limit the use of data. So these regulations are very necessary, but they can push towards a one-size-fits-all um, kind of data governance in organizations. And there's this very interesting paper from Delacroix in 2019 that says that, and proposed to have what he called data trusts, or it's some kinds of unions that represent individuals, but different views of privacy and different risk appetite with their data. So maybe I I'm very sensitive about privacy, but maybe George is not as sensitive. How can we deal with that if we have just one type of governance? So this is why it's an interesting idea to have that. kind of data trust or unions. A complementary idea is data dividends. So recently, you've probably heard about this man, Gavin Newsom. So he's the governor of California. And in 2019, he proposed an idea that would, for Californians that participate in uh, big tech platforms like Facebook or Google, they should have or they could have a cut of the revenues of these companies because they provide their personal information and these companies make money on this personal information. And a similar idea also in 2019 from senators in Virginia and Missouri proposed to force companies to value users' data and make this valuation transparent. And unfortunately, these ideas didn't go very far. The bill didn't pass, and the main reason why is because valuing data is very complicated and even more complicated since we have started this era of AI or machine learning. So in also 2019, Gobrady and Zhu in one paper and Jia in another proposed an approach to do data evaluation in machine learning, and it has four moving parts. So in machine learning, you usually have training data, you have the learning algorithm, and in data evaluation, you need to define your value function. So it's typically the accuracy or the mean squared error or the F1 score evaluated on the test set. And you need a valuation method to value each data point in the data set. And in both of these papers, what they propose is to use Shapley values. And I'll give more detail in the background later on. So now the problematic that we're interested in is data valuation for compensation. So this idea of an organization doing data valuation to maybe implement the data dividend idea. So let's say that individuals provide their data to an organization. The organization do data valuation. It assigns shares to each individuals. And then he realized that some individuals, they don't participate or contribute very much in the machine learning models. So he decides to remove them and says, well, only these ones should be compensated and the others should not. And we think it's a problem because it underestimates the fact that to get these insights, the organization had to collect all the data. So to do that evaluation with the data evaluation framework using Shapley values, you need to have all the data. And so the question that we raised is what is the hidden cost of data evaluation? And this is what we try to model or to measure in a way. And the approach that we propose is to have an information disclosure game. So it's a game between two agents, the data owner and a data consumer. The data owner represents the kind of teams you have in an organization who are in data governance, so they are more responsible for managing privacy. And the data consumer is representing more teams that really are trying to exploit data and to build machine learning models to achieve some goals. So one thing that we realized that sometimes confused people when I presented this work is data owner is not the individuals. It's really one agent that has all the data, but his goal is not to maximize utility. So here also what's important to understand is that in this game, the data owner doesn't release the raw data points, he releases noisy versions of the data points. So the data consumer, he needs to take decisions to acquire noisy versions and to acquire more noisy versions of the data points to achieve his goals, his utility goals. And we release these noisy versions of data points using what is called an epsilon differential private mechanism, and I will explain it more in the background. Another setup, so it's the same game, but like I said, since we realized that data owner sometimes is not very well understood in the literature, we're working at the moment on saying the same game would apply if we would think about data union or data trust like I discussed at the beginning. So, but in this case, it would be two different entities, but it would be the exact same game. So you would have a data union that collect the data and have the responsibility to maximize equity and protect privacy, for example. And the data consumer would be any organizations that want to consume this data. But it would be the exact same kind of game. Is it clear? Do you have any question at this stage, or maybe we wait until the end?
If someone has a question, the person will raise it. So,
Perfect.
but yeah, continue, please.
Perfect. So now a bit of technical background. So I talked about earlier about valuation methods. So there is a very basic or simple valuation method. It is what we call leave one out. So imagine that you have a data set, a database. You are interested in doing data valuation on one data point. What you can do is simply to build a second data set without that data point and train the model on both of these data sets, and you compute using any value function the contribution, and this is what we call so the marginal contribution or the leave one out value of a data point. This has been explored since 1977 by Cook, and he has showed that you can approximate this with influence function if you use linear regression models. But Gorbani and others have showed that these leave one out and influence functions have fragile interpretations, so it's hard to conclude anything in terms of value. And that's why Gorbani and Zhu, like I said earlier, and GI in another paper, introduced the use of Shapley values for supervised learning. And so instead of looking at only n subsets of the dataset, you will look at all the subsets, so 2 of the power of n minus 1 subsets. And you have to compute the Shapley value. So I'm sure that more people here are familiar with Shapley values, but it's the formula that you have here where this part is really the marginal contribution of a set. And what's interesting with Shapley values used for data evaluation is you can say, for example, that if a data point doesn't contribute to any subset of the data set, he will get a Shapley value of 0. If 2 data points contribute the same way to all the subsets, they will get the same Shapley values. Shapley value is decomposable, meaning that for data evaluation, if you have multiple test sets, you can combine the Shapley values of these test sets and to get the Shapley value of the combined test sets. And it has an efficiency axiom that says that if you do the sum of Shapley values, you'll get the utility of your data set. So you can see it as a more robust way than the leave one out valuation. But of course, it comes with a cost, a computational cost. So mostly the work that has been done in this field of data evaluation is to approximate these Shapley values, these data, what they call the data Shapley values, so the DSVs. And if you can see that you can, like other papers on Shapley values, that you can translate the formula into an expectation over partitions of the data sets. And one way to do it is to do a Monte Carlo simulation. And a trick that you can use for data evaluation is to observe that. So you generate, you can compute contributions of many subsets by first creating a random partition of the data set and then iterating over that random partition and computing this way the contribution of points. And you stop, that's why we call it truncated data Shapley values. You stop when you see that the contribution is too small. So it's a parameter of the approximation method. So that's one way you can approximate data Shapley values. Another way is to select a model, a machine learning model that is more simple, and that's what Gia did. So in 2019, she showed that for k-nearest neighbor, you can compute the Shapley values in an exact way in a linear complexity. And the insight on why this is possible is to realize that for k-nearest neighbors, you only need to look at the k-nearest neighbor for contribution. So any point that is further away, that the k-nearest neighbors will have a contribution of 0 if you select this valuation function. And so they arrived at this formula, which is a recursive formula that gives the data Shapley value of a point with respect to a query point or a test point. So now we're moving on to a different topic, because like I said, in this work, I use data evaluation, but also use a bit of differential privacy. So differential privacy is a technical definition of privacy that is very consensual in the literature. And the core idea of differential privacy is the principle of plausible deniability. And then what that means is, I'll show you with the small mechanism that you see on the right. So imagine that you are a participant in a survey, and we ask you the question, have you ever done something illegal? Instead of answering truthfully directly, what you would do in that randomized response mechanism, you will first flip a coin. If it's heads, you will answer truthfully. If it's tails, you will flip another coin and you'll answer no, yes or no based on if it's heads or tails. And in this way, if you get that information in a database, you can always deny that you answered truthfully. Actually, only 3 times out of 4 you will answer the right answer. And so this is what we call the plausible deniability principle. And differential privacy is based on that principle. Cynthia Dwork, she generalized that idea. And so the definition is a mechanism M is epsilon differential privacy for all neighboring databases, D1 and D2, and for all outputs O, the likelihood ratio of an output given the mechanism executed on 2 different databases, 2 neighborhoods, sorry, databases, is smaller than a quantity that is exponential epsilon, and the epsilon is actually the parameter of the mechanism. And it's sometimes also called the privacy budget, because the more that you increase the budget, basically the less privacy you get for individuals. What's also interesting in differential privacy is that it has roots in game theory. So it has an economic interpretation that was given by McSherry and Tawar in 2007 that says that epsilon differential privacy makes truth-telling an approximate dominant strategy. And if I can vulgarize this, it means that differential privacy bounds the incentive to lie on your information. In practice, how to transform any function into an epsilon differential private mechanism? Well, imagine that you have to compute the average. You have access to a database and you have to compute the average income that you get. you would first compute the average income. That would be the f of x, and you would add some noise using a distribution, here the Laplace distribution, parameterized by the sensitivity of the function, which is actually the maximum lim one out value that I explained earlier, divided by epsilon, which is the privacy budget. And this way you build a mechanism that is epsilon differentially private. Any questions so far? No, I don't see any hands. So I'll move on. Okay, so now I'll go back to the problematic that we're interested in, the methodology. So I discussed about the game earlier, about a data owner and the data consumer. And I wanted to show you that we started by modeling it as a very basic game, a pricing game between the data owner and the data consumer. So we can say that since the data owner sets a price and the data consumer gets this price, it's a two-phase Stackelberg interaction. And here, contrary to what I explained earlier, we wanted to see, okay, can we have that kind of pricing mechanism? And so unfortunately, we don't have a demand function. So what we assume is that both would assume the same machine learning model. So in our case, it was a k-nearest neighbor model. And also, we would assume that they both have access to all the data Shapley values. So we assume that we already computed the data Shapley values. And what we did is we defined a price per point that is equal to the base price, which is, we picked the Shapley values, plus some costs that is a function of the Shapley value, but also a parameter that the data owner needs to decide on. And so the data consumer, he only has to decide what point to acquire. And of course, he wants to achieve his utility target. And so the data consumer wants to minimize his costs, and the data owner wants to maximize the minimum payoff he gets from the data consumer. We didn't go very far with that approach because the problem is we didn't know which data point we should penalize or reward. So we couldn't find a solution where some points will not be excluded, which is part of the problematic we're trying to tackle. So that's why we moved on to this partial disclosure game, where it's a similar setup, but instead of a pricing game, it's more the data owner release noisy versions of the data points, and the data consumer have to decide if he wants to acquire them to achieve its goal. So here, what's important also to understand is that the data consumer doesn't have access to the data Shapley values. So to understand what data points he needs to, noisy versions of the data points he needs to acquire, he needs to do data evaluation, or he needs to find a strategy that allows him to minimize his costs. And so this is what we expect model as the objective is. We want to minimize the number of time so the data consumer wants to minimize the number of time he queries data points multiplied by the budget. And the data owner, he wants to maximize this minimization. And of course, there's still this constraint from the data consumer on the utility target, sorry. So basically, the data consumer would stop once he achieves his utility target. Right. So now I'm moving on the experiment. So we decided to pick on the task of classifying online customer reviews. So I'm sure you're already familiar that it is a big thing online when you have interacted with platforms like Google Reviews, Yelp, or even Amazon. And the idea came because I I watched a documentary, or I don't know how to call it, of Radio Canada that explained that it has become so big for businesses that now they really pay attention to helpful versus non-helpful reviews. And if they judge that a review was very bad for their business, they even sue the customer that made that review because they say that they had repercussions, financial repercussions because of it. So for me, it made a lot of sense to apply data evaluation to that task of predicting if a review is helpful or not. And so this is what I try um, to study. So predicting review helpfulness in our case, since I said that I use k-nearest neighbors, would be that we picked an open data set, the Yelp data set. We found a benchmark from Bilal in 2022 that used transformer to predict this task, to solve this task. And so we used the exact data set that they prepared, and we tried different sets of what we call BERT embeddings to use k-nearest neighbors on top of it. So the embeddings is just a way to encode unstructured data, so textual data. And this way you can use very basic model like k-nearest neighbors. And we just verified that the performance of this k-nearest neighbor was on par with the performance that they use with transformer models in their paper. And we managed to achieve it because there's been so much research recently on embeddings that a simple k-nearest neighbors was giving us very good results. And like I said, the objective is to predict if one of these, actually a test, a review in the test set or the validation set is helpful or not based on the training set. So we started by just reproducing the data Shapley evaluation task that we can find in papers like Gorbani and Zhu and Jia, which is you acquire, you kind of simulate the data acquisition process. So you will start by, okay, so the black line is a random strategy. So you would say, I will acquire random 10 points, 100 points, 200 points, and see how my accuracy, which is the way that we evaluate the utility of the model, increase. And you can see that if you repeat that experiment multiple times and you compute the mean, the accuracy increase towards the utility of the whole data set. But if you use the KNN data Shapley value, so you order the data sets using the Shapley values, and you use that as a strategy for acquisition, you'll see that you'll get actually higher utility, and you don't need the whole data set to achieve a high utility. And also, you can detect the points that if you remove them, you actually get a bit. That's the points that really decrease your utility, and that's why we get a better utility with Shapley evaluation than by just acquiring the whole data set. So that's just a reproduction of the same experiments that we find in data Shapley values paper, but for this task of predicting review helpfulness. So now back to our problematic. So on the left, the data consumer, he tries many uh, um, random acquisition strategy. And so we plotted um, the results for each random acquisition strategies. So each line is so you can see that if you so to remind you the game you release, so it's a different uh, setup than the slide just before, because here we're back into our own problem where we in the game we release noisy version of the data sets. So the iteration here is the iteration of noisy version of the data set. So if you get to 100, you actually get very close to the actual data set. If you are at 0, you get very noisy version of the data set. And so the strategies are, if you acquire a percentage of points, let's say I commit to 20% of acquiring, I commit to 20% of the data set and only 20% of the data set. This is the kind of curve that you will get, and you will not achieve your utility target that we evaluated so about 0.7 targets. And so you need 100 iterations and almost 100% of your data set to get to your target. Now, if you use Shapley values as a strategy, you'll see that we observe that we only need 10 iterations to achieve the targets, and a small percentage of the data points to do that. So already, like Shapley values, in the game that we offered earlier, that we proposed earlier, is a better strategy than random. So if the data consumer do data evaluation while he acquired points. But we tried a more sophisticated approach. So not just using Shapley values, but we said, okay, maybe the data consumer, he look at data points like uh, casino slot machines, and he wants to estimate the value of each data point. And he has this dilemma of exploring versus exploiting data points. So the way that so if he thinks that he gets closer to the actual value, he knows better what kind of decision he can make. And it happens to be pretty much the problem of a multi-arm bandit. So as a strategy, we picked multi-arm bandit as well, using an upper confidence bound with the budget constraints. I'm not going to go into too much details, but what we observed is similar results than with the data Shapley value strategy, uh, in the sense that if we fix a maximum budget per arm, so if the data owner fix a max budget per arm of 20, the data consumer is very unlikely to achieve his target. And so it's a minimum maximum budget per arm that he can set. Otherwise, the consumer will not acquire any data points. And another insight that we got from this strategy is that the data consumer can get lucky and achieve his targets by focusing on very specific data points, but it's very unlikely. And the way we measured it is we computed the Gini index on budget consumption, so the differential private budget consumption. And what we show is that the more he spread the budget, the more likely he will achieve its targets. As a final experiment, but this is more related to the rest of my research, is we wanted to evaluate if this happens, if this game happens inside an organization, if we build a model on top of the noisy version of the data set, are we more privacy preserving? So if we publish the model like through an API or some sort, is it possible to re-identify individuals or to prove that an individual was part or not of the dataset? And so it's I'm not again not going to get into too much detail here, but it's called membership inference attacks, and we just wanted to know, is it better to release a k-nearest neighbor on these noisy versions versus on the full dataset? And it is, but it doesn't really remove completely the privacy risks. Uh, but this only works if we consider that game inside an organization. It doesn't really work if we look at interaction between a data union and a data consumer. So this is it for the experiments. So a couple of key findings. So our information disclosure games makes the hidden cost of valuation explicit. So through the differential privacy budget, and this was part of our analysis of if we have if we can create an incentive to acquire points or not. Both Shapley-based and bandit strategies require a minimum exploration budget, around 20 iteration from our experiments. Larger budgets spread value more evenly across data points, so it creates more inclusiveness. And actually, in the first iterations, the data consumer, he acquires all data points, so there won't be any individuals left behind. Even if their contribution is very small or even negative, they will get a little bit of shares. The limitations is we only looked at k-nearest neighbors, so we are planning to move on more complicated models like neural networks that comes with more complexity, especially computational complexity. And we did not we made some assumptions like the data consumer is not going to try to really re-identify people to get some external information on which point he should prioritize. And so this is also part of the further work that we want to mitigate this problem, and also work on more sophisticated release strategies like synthetic data using like a machine learning model. So this is it for me. I repeat that I'm really planning to continue this work and hoping that you give me feedback. Uh, this is the reference. I will share the presentation if you're interested. Don't hesitate if you have any questions.